So this is another video on proving some things that kind of belong to modern algebra, but they're proofs that we usually skip over in a modern algebra course. Again, mostly because the tools we use to prove these, they don't really demonstrate modern algebra, abstract algebra kind of things. And so these are, for instance, I always quote laws of exponents to my students, but I don't typically prove them. The way we're going to prove these things is by induction. Okay, so let's get started. The first thing I want to show is that if you have a to the n times a to the m, this is a to the n plus m. Okay, so this is in the context of we're going to assume that we have an associative operation, and that's all that we need to begin with. Okay, so let me go ahead and show that this works for all positive integers m and n. And so what we're going to do is to prove this by induction. Okay, so we go, first of all, base case. The base case, an times a to the first. Well, okay, what do we even mean by exponentiation? Well, it's actually defined in this way. A to the first is defined to be a, and a to the n times a is defined to be a to the n plus 1. You actually define exponentiation inductively. Okay, so that's actually, if you ask what is a to the n plus 1, it's a to the n times a. And you can unwind that all the way back down to from, say, a to the 10th to, that's a to the 9th times a. What is that? Well, that's a to the 8th times a, all the way down where a to the first is a. Okay, so our base case holds where we can add exponents. Okay, now we make our inductive hypothesis. Okay, so let's suppose that a to the n times a to the m is equal to the a to the m plus n plus m for some m that's at least 1. Okay, so we're going to assume it holds for m. I want to show that it holds for one more. Here we go. Okay, well, consider a to the n times a to the m plus 1. Okay, well, by definition, this is a to the m plus 1 is a to the m times a. Okay, I can now use my inductive hypothesis to say that, okay, that's a to the n plus m times a. All right, that's my inductive hypothesis, because m is, I've assumed it holds for m. Okay, and then I use the definition of exponentiation, of exponents, and say, okay, if I multiply this by a, I'm adding one more. And notice we have our law of exponents. If it holds for m, it holds for m plus 1. And so by induction, we have that this law holds for all n and m at least 1. Okay. Now, we actually know this holds more generally than that. Well, if we have extra tools around. So now let's assume that we have an identity. Okay. And since we're writing things multiplicatively, let's call this identity 1. Okay. So then if we have a multiplicative identity, we extend our definition of exponentiation to say that something to the 0 power is defined to be 1. Okay, and so what we can do now is to adjust our proof. And so here we go. Our base case now is 0. And that would be the identity. And if you multiply by the identity, that doesn't do anything. That is the definition of being an identity. And so this is a to the n plus 0, right? And there we go. This now holds for m equals 0. Okay. Now assume that we have this holds for some m greater than or equal to 0, and the rest of the proof goes through, no problem. But now we can say this holds for all n and m greater than or equal to 0. Okay. But you need to have a multiplicative identity to even talk about that. Okay. You may go, okay, well, hold up. How about inverses? Okay, well, now let's add in even more. Let's say that we have associativity, we have an identity, and let's assume that A has a multiplicative inverse. And so we already know that when you have a two-sided inverse, it has to be unique. And so we're going to call that guy a to the minus first power, right? So that minus one exponent, that we use that as like, that's a definition. That exponent goes with a's inverse, and we know that that's a unique thing. By the way, I need to extend the notion of what exponentiation means in the case that I have negative exponents now. And so for some n greater than or equal to 1, I need to explain what a to the minus n means. And so let's go ahead and define that to be a's inverse to the nth power. And we already know how to take something and raise it to a positive exponent. And so there we go. We now have a to all integer powers that's defined. So in particular, if somebody said a to the minus third, we know that's a to the minus first cubed. And by our definition, that's a squared times a to the minus a inverse squared times a inverse. And this, by definition, is a inverse times a inverse. Well, a inverse to the first. And so ultimately, that's just 3 a inverses multiplied together, just as an example of what we mean by raising to a negative exponent. Okay, so say that we're now in this context. I want to now prove that this law of exponents holds not just for all non-negative integers m and n, but holds for all integers m and n. Okay, so we're in the context where we have an associative operation, we have an identity, and our particular symbol has an inverse. And so let's go ahead and try to tackle that. Okay, first, before I get into fixing my proof, I need a kind of partial step, like a little bit of a lemma. So first thing, I just want to show that I can go one up and one down. Okay, so let's let n be any integer power now, and consider an, and look at this to, I want to multiply this by a to the first, and I want to see that that is indeed an plus 1. Okay, and then likewise, I want to show that if I have any integer power and I multiply by a inverse, that this is a to the n minus 1. I need to show these things. Okay. Now, let's tackle this guy first. Okay. Well, first of all, for n greater than 0, check. That's just its definition. All right. So we know that if this is how we defined exponentiation. For n equals 0, well, again, check. That's just a law of exponents that we've already proven. But in particular, if n is 0, this is the identity times a, which is just a, which is the same thing as a to the 0 plus 1, or a to the first power. So we're good there. The case that we need to worry about is when n is negative. So let's suppose that n is negative. Well, if that's the case, we have that what is a to the n? By definition, a to the n would then be a inverse to the, I'll say, magnitude of n power. Right? Okay. So that's what that would be. In the word times a. That's what a to the first is. Now the thing is, if n is negative, this is at least 1, and so we can pull off a power. We know this is the same thing as a inverse 1 less times A inverse to the first power. That's a law of exponents that we've already proven because it's only involving non-negative powers. Okay. And we can then use the fact that A inverse is A's inverse, cancel these off, and we end up, so this right here is equal to 1, the identity, and so this is A to inverse to the magnitude of n minus 1 power. Okay, now what is this? Well, by definition, that is A to the, okay, and this works out to be negative n plus 1. Okay, because we're that, and this actually, yeah, it works. That's by definition what this is, because A to the minus first raised to, this is some non-negative power, is A to the minus that power, and in particular essence. So now we have that we can move 1 up. It's a little tricky, but there we go. And now let's see that we can do 1 down. Okay. So what about going 1 down? Well, here we have the opposite issue. If n is negative, then this is actually the definition, because this would be A inverse to some positive power times A inverse, which would be A inverse to 1 power more. Okay. N equals 0. Well, again, we already know this is true because A to the 0, that's the identity. Identity times A inverse is just A inverse. And this would be, that's the same thing as A to the 0 minus 1, that's just A inverse. So this is evidently true for n equals 0. So it's the last case where n is positive that we need to worry about. Okay? So let's suppose that n is now positive. All right, well, if n is positive, then A to the n times A inverse. Since n is positive, I can rewrite that as A to the n minus 1 times A to the first, because this is non-negative. That's using the law of exponent, either the definition or a law of exponents when n is 1. Anyway, we already know this case. And here we have A times A inverse. That's the multiplicative identity. And so by definition, so anything times multiplicative identity is itself. And there we go. Now we have established going down 1 for an arbitrary A to the n. Okay, so we have our little lemma behind us. Now let's go ahead and prove our law of exponents in the final case. So here we go. Suppose n is an integer, and we'll say that, note, here's our base case. We have A to the n times A to the 0 is A to the n times 1, which is A to the n, which is A to the n plus 0. There we go. This holds for 0. Okay? We already knew that, but we'll just write that down again. Okay, now I want to show that this holds not just for 0, but for all integers m. And so I'm going to have to induct up and induct down. So first of all, suppose that m is greater than or equal to 0, okay? And A to the n times A to the m is A to the n plus n. This is our inductive hypothesis, okay? Well, let's show that this now holds for one more. Okay, am plus 1. Well, by definition, this is am times a, because these are non-negative exponents. We know that that's either by definition or at least using a law of exponents when m is 0 that we already know. Okay. Now I can apply my inductive hypothesis, that's A to the n plus m. And then I can apply my little lemma that says, if you multiply this by A, you move up by 1, okay? Which could end up being the definition of exponentiation, but maybe not if this involves like a negative exponent or something like that. Okay. But in any case, what have we shown? We've shown that if this holds for m, it holds for one more, and so therefore we have that this now holds for all m greater than or equal to 0. That's what induction gives us. Okay, let's modify. All right, base case, we still have that. Now let's suppose m is less than or equal to 0. Okay, well, we're going to assume this holds. This is our inductive hypothesis. Okay, let's go down by 1. We apply our lemma that says that if we take am times a inverse, that moves it down by 1. So that's using our little lemma that we can go down by 1. We apply our inductive hypothesis, boom, there, to say that am is an plus m. Then we once again apply our little lemma that if you multiply by a inverse, you take the exponent down by 1. And there we go. Now we have that if our result holds for m, it holds for m minus 1. And so we have that it holds for all m's less than or equal to 0. So we've inducted up, inducted down. We now know that this holds for all integers n. Okay. How's that for pretty tedious? All right. Let's go to another law of exponents, okay? Again, this is another one of those ones where I'll just say that it holds and I won't worry about it. But let's go ahead and prove it. Okay, a to the m, a to the n to the m power. All right, okay. First things first, let's do this in the case where we just have associativity. All right. And so these guys are positive exponents. All right. Well, how do we do this? Well, let's see. If we have, we'll do an inductive case, an inductive proof. We have our base case. That's just the definition, a to the n to the first power, just a to the n. And that's the same thing as a to the n times 1. Okay, there's our base case. Let's suppose that this we have a to the n to the m equals a to the nm for some m greater than 0, some positive m. Okay, and we want to show that it holds for one more. So consider a to the n to the m plus 1 power. I now apply our definition, really. Okay, that that this is a to the n to the m plus 1, that's a to the n to the m power, and times 1 more. We use our inductive hypothesis. That's a to the nm, right? Then we're going to use the law of exponents that we have just proved that we can add. And so this is a to the nm plus n. And then if we rewrite that, that's a to the n times m plus 1. Okay. And so what have we just shown? We've just shown that if this holds for m, it holds for m plus 1. And so therefore, by induction, this holds for all n and m that are positive integers. Okay. Now, what if we have an identity? Okay. Well, then this makes sense to chuck in 0. Okay. Well, now our base case. That's pretty easy, right? Okay, now we just write it down for 0 and throw in suppose this holds at m equals 0. This shows that it holds for one more. And now we have it holds for all non-negative integers. Okay. What if we have an inverse for a? Okay. Now let's assume that we have an inverse for it called A inverse. All right. Well, now I want to show that this holds for all integers n and m. Okay. Well, I have my base case. And what this goes to show is that I can move up one. So we have we're inducting up, right? And I don't really need to change the proof because at each stage, I'm using like stuff that I previously know. Now I'm kind of using the law of exponents, that this to the m plus 1 is this to the m times this to the 1, the first power, inductive hypothesis. And this right here is using our law of exponents, which we know in this context holds for all integers m and n. Okay, so if it holds for m, it holds for one more, that inducts up. Now we have it works for all m greater than or equal to 0. Okay, let's now let's go down. Okay, m is less than or equal to 0. And we'll put a little m minus 1 there. We put our minus 1 there. And so I'm going to put a little minus sign here. There's something that I need to prove to get this. I need to show that a to the n inverse is a to the minus n power. So we'll prove that in just a moment. But if we have that, then we apply our law of exponents. We go down by 1, and now we have this holds for all m less than or equal to 0. Okay. So finally, let's go ahead and prove star, and then we will have a complete proof. Okay. So last lemma. I need to prove this. Okay. All right. Once again, we're going to do this by induction. Okay. So first thing, if we have n equals 0, the identity is its own inverse. And so this obviously holds in that case, right? Now, suppose we have that this holds for some non-negative n, okay? Then we take this. By definition, we have a to the n times a. We use socks, shoes. Remembering, flip around, take inverses. We imply our inductive hypothesis on n. So I'm assuming it holds for n. And then we use our law of exponents. And voila, we have that this is a to the negative n plus. And then finally, we need to have that it goes for negatives. So then we would need to go down. And so we just make our minor adjustment. The inverse of the inverse is the element itself. We use our law of exponents. There we go. There's our minor adjustment. And so now we know that this holds for all going up, all going down. We have filled in our proof, and we have our law of exponents. Okay. There's actually one more law of exponents that we often like to use, but this is suspect. We need the A and B commute, and let's save that for another video.